time on KNN, but actually a bunch of people have been asking me about question 5B on the homework, so I'm going to do a quick, we're going to look at that really quickly. Okay, so give me 1 second so I can pull it up. So 5B is about this procedure about dropping outliers. So I'll give kind of one hint here. What am I doing? Okay. Sorry, there we go. Okay, so question 5B was about how you would go about dropping points one at a time and then sort of doing this re-estimation procedure. So what I'll say is this is not something that we actually cover formally in class. This is not like a just plug it into a procedure type thing. And sometimes students will get upset that it's like not exactly how it's kind of described in lecture, which I get, but you know, this is applied data analysis, and really, you know, when you're doing real world problems, you kind of have to take the tools that you know and mold them in certain ways to be able to address problems that you have. And so this is kind of like practice in developing some of that skill set, is really getting exposure to being forced to do that sort of thing. So I will say this is a pretty, maybe slightly unusual way of doing things because it's not something that's like directly covered in class, but I will give a hint now on sort of how you would go about doing this. Okay, so I can't actually look at the problem at the same time. This does it? Can I see the printout again? Just want to make sure that I'm not misspeaking in any way. So like traditionally, right, we have our regression y equals beta 0 plus beta 1x, something like this. Okay, yes, this is fine. Yeah, this is fine. Okay, so the idea here is that we want to identify and drop outliers in a kind of a unique way. And we're trying to do predictions where you're actually doing a prediction on the explanatory variable as opposed to your response variable. So this is a little bit different here, right? So usually we would have something like a y hat. But essentially what I'm asking you to do is you're going to reorient this in such a way that you're actually going to be solving for your x hat. So you can set x hat and solve it based off of what you have in the rest of the equation, and then treat it like you'd be dropping these points one at a time. Okay? Does that make sense? Is everyone following along? Right. So you are essentially, what you're doing is you're going to be sort of reorient your equation, but you're not re-estimating, like this isn't like a new y, right? Because you've actually solved for your betas already. So once you solve this thing, you rearrange your equation to have this x hat is equal to, you know, your y minus beta 0 something like this. It's not going to be exactly like this, right? But you're not re-estimating these parameters. Okay. So this is kind of your starting point for this problem. Okay? Yes?
So as I was reading over, I wasn't sure, do you want us to drop from highest to lowest or lowest to highest or alternate between the two?
Drop data points from highest to lowest energy efficiency. Yep. That's all here. Okay, thank you. All right. So, jumping back over to here. All right. So, just as a refresher, the last topic that we talked about in Monday's lecture was about the k-nearest neighbors, right? And so I kind of gave the mathematical explanation for that, but the qualitative way this works is pretty easy, right? You just, for any point, you look at the nearest neighbors in your data set, the k nearest neighbors, right? If k equals 1, you only look at the nearest person. K equals 2, you look at the 2 nearest points. And whoever is the most, that's what you get classified as, right? So this, again, this is a type of classification example, right? So our y's are a categorical factor variable. And so let's look at an example implementation now of this in R. So we're going to use that Disney project or Disney data set that we looked at last time. So quick refresher, I'm just going to load all this stuff in. This plot, where's my mouse? Okay, here we go. So this plot that we saw from last time displays kind of the data that we're interested in doing our regression on. The y variable is our categories of movie ratings, or certificate ratings is what we call them, right? So G, PG, PG-13, and R. And then we have voter ratings, and then the runtime of the movie, and you can see how things change as movie runtime and voter rating changes. Okay, and so, you know, if I wanted to do a k nearest neighbors algorithm, okay, let's say I'm right here. So if k equals 1, the point where my finger would be what?
Blue.
Blue, yes, PG. What if k was equal to 2? Still blue, right? The 2 nearest neighbors are these two guys. What if it was 3?
Blue.
Still blue. 4?
Also blue.
Still blue, right? Because actually these two and these two, let's say those are tied, so it would go with the last one. What if k equals 5? Red, right? Because 2 blue, 1, 2, 3, let's say those 3 are the nearest neighbors, so that would be, now it would be red, because you have the most in red. Okay, you guys get it.
Alan?
Yes?
Can you repeat what happens if there's a tie?
Yeah, it actually depends on which algorithm and software that you use. So if you're a tie, let's say you're here, and it's a tie, sometimes it will do, so like 2 and 2, sometimes it'll do whichever one was last, and it's actually equivalent to another procedure, which is it'll look at the ones that are closest, which most of the time are gonna end up being the same because like those were the ones from the previous one, right? So yeah, ties will typically be the previous neighbor set.
Wait, can you explain, what was it when it was 3?
Yeah, so here, right here, closest, let's say, is 1, 2, 3.
Yeah,
So 2 blue, 1 red, so that's blue.
okay.
But then 4 blue, blue, red, red, now it's tied. So you're like, oh, what do I do if it's tied? You just look at the last one.
And the previous one was 3, which was blue?
Yeah, so then it's still blue.
Okay.
Yeah. You can, the other way to think about it is like, here it's tied, these two and these two, so which ones are closer? Have more, but that it's, it can get a little bit more complicated if they're like multiple ones and, that are like alternating where it's not as clear in, this case. Or it's more clear in this case. Okay, and if my, k is equal to 1,000,000, what would the color be?
Generation most.
Yes, exactly. So, I think it's either red or blue, but let's say blue is the most, then, k equals 1,000,000, this point is blue, 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 right? It's just gonna look at the 1,000,000 nearest neighbors, which is everything in this case. If I wanted to be more accurate, let's say, I can put my mouse, we would do something like, oh, well, it tells me up there 722. So if I have k equals 722, it'll be whichever dot has the most colors, and then everything will look like that. Okay. So how do we do k and n in R? So this code from before is just copy and pasted from last lecture. This I'm gonna save for later. Okay. Ooh, okay, wait, I need to do, before I do this. So k and n is based on the neighbors that are closest to me, right? So, before I run k and n, let's say this point right here, there's a neighbor here, and there's a neighbor here. Okay, which one of these points is closer to this point? You sure?
No, I can't really see it. I mean,
Okay, wait, okay, how about this? Let me ask this one. This point, okay, for this point, this is our home base. Is this point closer to here, or is this point closer to here? The top one or the one on the side? I see you pointing to the top one. Why?
Because it's like about 1 away or like 1
Mm-hmm.
and the near scales are different, I guess.
Yeah, the scales are different. Okay, so be careful about this, right? So here to here is a distance of like 1-ish. Here to here is a distance of like, what, this is like 25, so half that, so like 12, 13. Okay, does everyone see that? Our axes are different. So, if you were to run a k and n without adjusting for this, then the voter rating is going to totally dominate, right? Because these distances are so much farther apart because of the scale. So we want to adjust for that before we run the k&n. Okay, so I'm going to do that first. Disney dot normalized. I'm going to duplicate our filtered and I'm going to replace runtime min with scale runtime min, which is going to scale everything. And I'm going to do the same thing to rating. And actually, I need to get rid of this thing. We're going to replace that. There it is. So to explain what this is again, remember last time we wanted to look at every possible combination. So we did sequence from the smallest to the largest, sequence from the smallest to the largest, and then expand grid does all the combinations of those so that we can do predictions across the full set here. So this line of code is doing that. Okay, so now, so don't worry about line 18 yet. We're going to use that as part of the test set for our KNN. Oop. Wrong line. Okay, so there's a function called KNN that's going to run the KNN for us. We are going to train our model on, oops, we're going to train our model on the normalized data. So that's all I'm doing here, Disney.normalized, and I'm going to look at, you're going to put the explanatory variables here, so runtime and rating. And then, wait a minute. Okay. And then we can have a test. So test just means I want to put in a specific point and then make a prediction, right? So let's say, you know, if k equals 3, then what would the prediction be, right? And then it's going to look for this point at the 3 nearest neighbors and predict that. So that's what you put in test. But you can actually put in like a whole vector or a whole table in here, which is this Disney new thing, okay? So I'm going to predict every single point from this thing, which is going to do predict here, predict here, predict here, predict here, so on all the way up, move over, predict, move, and so on and so forth. Okay, so that's what is contained in Disney.new, and then we're going to predict over those. So that's going to look like this, Disney.new. CL is referring to your y variable. So those are the different categories for any, that should be corresponding to your training set. Okay, so this is how you enter your y.
What does CL stand for?
Good question. I actually don't know. Let's find out. Help KNN. What? And hang on one sec. Do I need to load in a library? Oh, yes. CL here.
Classification.
Factor of true classifications of the training set. Yeah, so that's your Y. Okay. So before we run this, we need, I forgot, extra, we need to load in the library called class. For some reason I thought that was a default. Okay. So CL, and then, you don't need to put this. Okay, so I run this, which I didn't load any of this in, so I gotta do that really quick.
What is the default K?
Oh, I did not put in K. Thank you. What do you guys want to do? How many neighbors do you want to look at?
5.
5. Okay, we're gonna look at 5 neighbors. It looks like the default is 1, but
Oh,
we'll look at that in a second, actually. Okay, so K equals 5. And let's take a look at a plot of that. So don't worry about entering this code for the plot. You can get it when I post it. But let's take a look at what the plot looks like. Wait a minute. It is because I don't know why this is happening. We want the normalized points. One second. Oh no, that's right. Right, because our spend one, sorry, one second. Disney.normalized. So one second while I troubleshoot. Oh, and while I put on my mic. So we are plotting. Okay, so ggplot, we're gonna plot kind of the background, Disney.new. Okay, so we have Disney.new, X is runtime, Y is rating, with certificate. What's that name? So for every point here, it's gonna have a prediction, which is correct. And then we superimpose the original normalized data on top of that, which also looks correct. Okay. So there's some weird stuff happening, and you know, you should always be kind of cognizant of this, right? So I'm not gonna attempt to totally fix this right now because I can't quite figure out what's wrong, but one of the things to keep in mind is like you don't want to just, you always want to have like a quick gut check to make sure things look reasonable. And actually for the most part that they do, but there are some weird things. I don't know if this is a graphical thing, but there's, right, you see these like weird blotches of red and blue. And so that kind of makes me suspicious. And one of the things that you can do, right, visually to check, particularly with a KNN, you won't always be able to do this. This particular problem that we're doing is set up in where I can visualize all 3 dimensions pretty easily. But, right, how can I check if this is correct, right? If I go into a blue area here, our K was equal to what? 5. So what are my 5 closest points? Like this, 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 and this. So these guys are all blue, so great. And then, yeah, I don't really know what's going on with these weird shaded ones. Actually, one second. I have a suspicion now. No, with K equals 5, it can't be a tie. I was thinking that maybe it's because the shaded areas are ties, but that can't be right because with 5, you can't have a tie. Okay, but anyways, you can always double check these things, right? I could like literally go to a particular point and look at the 5 that are closest around it. One feature that is kind of true of this is unlike with the logistic regression, these ones do not have a linear boundary, right? So this is like a highly non-linear boundary for any sort of like domain classification, and that is one particular feature of KNNs. So do the boundaries get crazier or do they smooth out? Oh, sorry. This doesn't have a clip today. So do the boundaries get smoother or do they get crazier when my K gets bigger? What do you guys think? Smoother, right? So as I look at more and more neighbors, eventually it all becomes one color, right? Whereas you can imagine if I were to do K equals 1, like this would be red, 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 then it would change to purple, right, as I got closer to the single point. And so then you would have kind of surrounding every individual point its own kind of color boundary, okay? And so we can take, maybe we can take a look at that if the next plot works.
What was K for this plot?
K was 5 here.
Just 5.
Yeah. So again, don't need to follow along here. This will be posted shortly. So this is, we're gonna look at K and N across a range of different Ks, and I'm just running them. All right. No microphone today. So I'm running K from 1 to 10 in a for loop using that function that I just showed before, and all I'm doing is I'm setting K equal to the K value in the for loop, okay? And I'm gonna plot that. So let's take a look at what that looks like. So we looked at K equals 5, and now we're going to look at K from 1 to 10.
What was the L equals 0 after the K in the code?
Oh, yeah, so that was, it's a setting that has to do with minimum number of points to do a classification, but it's by default equal to 0, and you don't need to worry about touching that. In fact, you could just ignore. You don't even need to put that when you're running a K&N. Okay, it's plotting. Takes a little bit of time because it's a lot of points that you're trying to plot through. So hopefully. Okay, and while we're waiting for this to finish up, this is going to kind of conclude our discussion about k-nearest neighbors, but this is essentially like a different sort of very nonlinear, non-parametric example of a classification. It's kind of like almost on the opposite end of the spectrum as the sort of logistic model, which has certain types of constraints in order to constraints in the way that it classifies things, right? It's got those linear boundaries. So, yeah, here is K equals 1, and you can see that like as I get close, as soon as I get away from a particular point into another color, it sort of changes the color, right? And you can see you can imagine what crazy stuff is happening behind those points, and then as you increase the Ks, actually the number of, you're actually going to be decreasing the number of like different boundaries until eventually you get to 1. I mean, in here there's like 700 points, and so I need to run K equals like 722, whatever it is, to get all the way to that point, but you can see how sort of different clusters or different choices of K end up giving you sort of different classification solutions. And so, how do we choose K again? What's the best way? Cross-validation, yeah, exactly. So, imagine, right, so conceptually what we would do in a cross-validation, let me just take away a handful of these points away. Okay, and then let me put a point back in and see how good my particular classification does compared to another classification, compared to another choice of K. And you want to find the one that essentially predicts the best out of sample. And that's how you would choose your K. So, which one do you think will have a lower error rate? And by error rate, I mean which one will classify my factors better? The logistic regression or k-nearest neighbors? What do you guys think?
Which will have a lower error?
Yes. Any ideas? So generally speaking, right, the kind of flexibility that you have in a k-nearest neighbors inherently means that the KNN, if you do the like cross-validation thing, right, should have at least as good as, if not a better classification, successful classification rate than a logistic regression. But the KNN does not give us the same sort of qualitative inference that we can make as a logistic regression does. So this is kind of very analogous to things we're going to be talking about from like our simple linear model versus a more complicated like spline or kernel regression, which we'll be talking about later. But there's a reason why people still do like linear regressions all the time for ease of interpretability, right? Like this is the thing about how I can interpret a beta coefficient as a slope as opposed to like a squiggly line, right? With a logistic regression, I can say something about the probabilistic outcome, or how likely it is probabilistically for the classification to occur, right? Remember the sigmoidal curve. Whereas here you don't really have any of that. It's just like it's this thing or not, right? So those are some of the trade-offs that you need to think about making if you want a more like inferential model and be able to say something about like interpretability as your x's change, what happens to y, versus with like something like this where you care most about the prediction outcome, okay? Am I making sense to people? Is this, yeah?
So it's probability versus prediction ability?
Kind of, but the probability example with logistic versus this is just like one example, right? It's more, I would generally classify that as like some sort of inference. So like another analogy might be, do I care about prediction in a non-parametric model versus interpretability of like a beta coefficient in a linear regression? Yeah. Okay. All right. So the rest of lecture today we're going to be doing something a little bit different. Let me, where's all this? Okay, so we're going to be talking a little bit more conceptually today. We are going to focus on, so there actually is, this is all going to be conceptual today, so there isn't going to be any R examples associated with what we're talking about today. And we're going to be talking about causality. Most of the lectures that I have so far, then I kind of make these homemade notes and they're all available for you guys on Canvas. I don't have that for this material. It's new material, but it's all derived from this textbook, which is actually all online. So I will give a link to that textbook, and you guys can look at the chapters that I point out for this material. Okay, so correlation does not equal causation. And I'm sure you guys have all heard this before. This is probably not groundbreaking, but I really want to spend some time to really think about what that means, especially in the context of the way we think about regressions and regression results. Okay, so correlation is the relationship between two variables, and causation is one event is the result of the occurrence of the other events. Okay. So these two things are different. And one of these things, the like correlation effects, are really kind of what we've been talking about so far, although we really haven't differentiated correlation and causation in any of the results that we're talking about. So to make this really concrete, I'll give an example. This is kind of a silly example, but this is one that we covered in the class, right? So we did that wages example, okay? And we talked about how wages are a function of race, age, education, and gender, right? So what did we find about the differences in wages between males and females in that data set? Females were much lower, right? And so, okay, is that a causal effect or is that a correlation? Correlation. Well, yeah, okay, we don't know for sure, but we haven't kind of done necessarily the work to demonstrate that it's causal, right? And how might you do this? Okay. One of the ways that you might suspect that it's not causal is you could perform a test, right, to see that it's not causal. This is kind of a, again, silly example, but if someone in that data set were to just change their gender, right, and go from female to male, would they like automatically get, what was it, like a $21,000 change in their income? Right, that's, so if you're thinking to yourself, no, that wouldn't happen, right? That's kind of what we're talking about with causality, we basically want to say, we want to figure out that, you know, if a particular thing in X changes, it will directly lead to a change in Y. And that can be really hard to figure out. Okay. So, there's this kind of interesting example in this textbook. So this guy, he's got a dog, and every night he goes to sleep, and when he wakes up, he sees his dog digging up his flowers in the garden outside. And he thinks to himself, well, the dog must be escaping through the front door. And so, how might you test that the dog is escaping through the front door?
You close the front door and the dog's there.
Yeah, okay, so you close the door and you lock it, and then you go to sleep that night, and you wake up tomorrow and you see if the dog is outside, right? And so this guy does that, and he closes the front door. Okay. And the dog the next morning is still in the garden. Okay. So, what does that mean? What was that? Yeah, the dog was getting into the garden, maybe not through the front door, maybe through something else. Right? And so, you know, you may have all of these alternative paths in which the dog is taking to get outside. And so you can kind of close them one by one. Okay, so I'll close the chimney, close the side window, I'll close the other side window, I'll lock the basement, I'll lock the back door, and eventually, as you do these tests, you figure out, okay, the dog is no longer outside in the morning, and you have identified the culprit that the dog was using to get outside. And you've done this by doing these sort of direct tests, right, to figure out like almost a direct cause and effect. So, identification. So this is the process of figuring out what part of the variation in your data answers your research question. And this is kind of one of the most underlying principles for causality research, the process of identification. And, you know, in econometrics, especially econometrics, there's focus on understanding causality. Identification is basically the process with which we do that. Right? So by closing avenues of escape, we are identifying the answer by controlling every possible explanation. And that can be fundamentally difficult, okay? Controlling every possible explanation. That's one of the things that makes causal identification very difficult because, like, do we have data on every possible explanation? Probably not, right? So there are some nuanced strategies that people take to really help address with this particular problem, and we're going to talk about that next class. Yeah, so we will learn some of the statistical tools for like closing those doors. And I'll just kind of point out that at the end of the day, any identification process will require you to make assumptions, okay? It's a necessary part of like putting a model together, doing data generation, right? Like, if you thought that dogs could teleport, or that like the universe was like a hologram and that the dog just walked through the wall, right? You would quickly exhaust your ability to include those as possible explanations, okay? So that fundamentally means that when I'm trying to do an identification process, you are always inherently making assumptions about the way the world works. And there's no way around that. Okay. Questions? So we're gonna, oh, yes.
Since we're in the theoretical part, that's where literature review might come in. To say this is, because it would be like infinite variables, and kind of how you boil it down to the ones that you think, based on your assumptions, that are literally backed by years. And how you boil it down to this is the ones that I think.
Yeah, so other research, other studies can help inform part of that worldview. There's going to be specific techniques that we take to try and address some of these things. But yeah, like, you should be prepared to defend any kind of assumption that you're making, right? And so some of these might be easier, like, I've never heard of a dog teleporting before, right? And so maybe that would be easier to justify. But there could be other things that might be more difficult, like how do you make sure that, you know, how do you know that dogs can't unlock a door? Because some dogs probably can, right? And so you run into these issues where if you close all of these entrances into the house, but the dog still appears outside in the morning, you're like, well, it's something else, right? Like, it's not any of these things because I've tested these things. Therefore, it must be that the dog is teleporting, right? But really, the dog knows how to open doors. Yeah, so you have to be prepared to defend your assumptions. Okay, but back to more like fundamentals here. The way in which we're going to try and formally attempt to, or like systematically try and do this, the most common way is through something called causal diagrams. Okay, so causal diagram. So this is a graphical representation of causal relationships. Okay, so some ground rules for this. So variables are represented by nodes. And causal relationships are represented by an arrow from the cause variable to the caused variable. Okay. X to Y. So X causes Y. Does anyone have any examples that they can think of? One thing leads directly to an outcome.
Rain, wet.
Okay. Yeah.
That's a sweet choice. Hungry, eat.
Sorry.
Human behavior, hungry, eat. Whatever works.
Well, okay, let me just do yours. Okay. Rain going to you being wet. Yeah. So this is like a cause and effect thing, right? If it rains, you can get wet.
That's, I mean, it's kind of a cyclical, that one is actually a lot more complicated.
It could be. Well, why?
Cause like, the water cycle is like, kind of that evaporative thing goes back into the clouds, you know, like how.
Yeah.
It's being complicated, but it is kind of like, a wetter area can also be like the cause of rain.
Yes. Although I think you were talking about like just someone getting wet.
Yeah.
Is that right?
Yeah.
The ground, right? If it was the sea, it was already wet, or it
Yeah,
was like,
right.
I kind of bounded it to
Yes.
very
Um,
simple.
yes, sure.
Time frame.
Yeah.
Yeah, I just overcomplicated it.
No, that's fine. And in fact, this is kind of what you need to be thinking about when you're doing stuff like this. Although, okay, one thing I will say is that for causal diagrams, we want to avoid cyclic things. So you should never have arrows that go back and make loops. And there are a couple reasons for that. But generally, as you set up these diagrams, that's something to avoid. your hypotheses are gonna be directional for a lot of this stuff. Okay. Is rain the only thing that could get you wet, right? So like, if you see someone who's wet, you're like, ah, it must have been rain. Huh?
If it be the ground, it'd be easier. If it's a person they sweat or.
Well, okay, let me just say, okay, for this
Like,
example,
person.
let's do this. Um,
So no, it could be exercise and perspiration.
okay, yes, so there could be all this other stuff. Okay, exercise, let's say there's a pool, you know, shower,
Ice bucket challenge.
yes, ice bucket challenge. So, just because it rains doesn't mean that's what caused someone to get wet, right? You could have a bunch of other possibilities, and so we call these unobserved variables. And so this might be a U, so this is unobserved, and this could be something that affects, you know, either your explanatory variable or your response variable. And actually, we typically still want to include this in the graph, even if we aren't able to necessarily observe these things directly. And so, one of the things that we're going to want to do is, as we control for certain things in certain ways, it's going to let us control kind of the flow of information in certain directions. And that's why you want to make sure you want to include everything as much as possible in your causal diagram. So I'll give another example of this. So what is the relationship between shorts and ice cream? So there is a relationship between these two things, and that might come from an unobserved thing. And so in this case, people are more likely to wear shorts on days that they eat ice cream, right? So on hot days, you would wear shorts. You're more likely to wear shorts, and on hot days, you're more likely to eat ice cream. But does shorts cause ice cream? Does you wearing shorts cause you to eat ice cream? No, right? And so you can see how we are setting up the design of our causal diagram to logically explain how we hypothesize variables influence each other causally. Okay? So in fact, doing some kind of regression model where you have shorts and ice cream, you actually might see a direct relationship between these two things, but it doesn't mean that they're causal. And the reasoning for that is there is some unobserved effect happening that is leading you to see that correlation, even if it's not a causal relationship between those two variables. Okay, any questions so far? Yeah, so you need balance here, right? So in terms of what you want to include, because if you omit too little, many things end up looking causal. And if you omit too much, you might miss the causal variable. And get identification wrong. Okay? So you want to develop a defensible hypothesis and assumptions. Okay. Let's talk about a couple of specific types of things to consider in your causal diagrams as well. So we might have something that looks like this. So x going to y and z going to y, and this would be, there are cases of this where we would call this a moderator variable. Okay, and so this is where z modifies the effect of x on y, but is not causally related. So this is one tricky thing that you may have to think about. Including in your models. So an example of a moderator variable would be fertility drugs and getting pregnant. Okay. So who thinks fertility drugs can have a causal effect on your ability to get pregnant? Raise your hand. No one, really? You guys don't believe in medicine? Yes, okay, so this is an example of a cause and effect type thing, right? So if you take fertility drugs, you may have a higher chance of getting pregnant, and we're representing that causally through this linkage arrow. Yes?
So then is there a difference between cause and probability then? Because just because you're taking fertility drugs doesn't necessarily mean.
Yeah, okay, good question. So that would still be a cause and effect, right? So yes, causal things can be probabilistic effects for sure. Yeah, so that is one important consideration, and oftentimes it's kind of we think about this as a more aggregate thing, and then it would be probabilistic for an individual. And so what I mean by that is like, say you have a cohort of 100 people and another cohort of 100 people, and then you give these 100 fertility drugs, and you give, so, fertility, and then no fertility. And then this leads to 60 people getting pregnant, and this leads to like 30 people getting pregnant, okay? So we would say the causal effect here would be like a increase in number of pregnancies by some amount. Yeah, question?
If it's fertility drugs for men,
Okay. So,
and then they impacted women,
yes. So the moderator variable, which you're kind of getting to here, is that you have a uterus, right? So, X on Y, so Z modifies the effect of X on Y, but it's not causally related to how X causes Y. That's an example of a moderator variable. So, yeah, so the moderator variable in this case of having a uterus isn't like affecting the drug mechanism in any way, but it is affecting the causal impact of fertility drugs on your ability to get pregnant. Okay. So, any questions about this? Okay. So that's one kind of thing to think about, is if there are any moderating variables.
Are moderating variables generally associated with things that can be factors? Or is that just this example?
No, not necessarily. Yeah. No, a moderating variable, I'm really bad at like thinking of these examples on the spot, but a moderating variable could definitely be like a continuous variable. Doesn't have to be a factor variable. I can't think of an example off the top of my head, but
well, I think this one is, because each organism is different, and the medicines affect each organism different, so it's not continuous, it's not binary.
no, that's not. No, but the moderator variable itself. I mean, the causal.
And if you don't have any uterus, there's no way you can get pregnant.
Yeah. So in this case, the moderator variable is very clearly a factor variable. It's like you have a uterus or you don't. Even if the like causal effect is the causal effect would be like probably a continuous thing. Okay. So there's lots of things to think about as you construct these diagrams. And so one of the things that we want to think about is how you might simplify. So simplifying your diagrams. And again, these kind of boil down to making assumptions about certain things, but one, unimportant. So if arrows are tiny or unimportant, you can probably remove them. 2, redundant. So So if variables have the same arrows coming in and going out, you can combine them. Right, and so if you have something like A going to B, C going to D, you might think about combining B and C. 3 mediators. So if one variable is only on the graph as a way for one variable to affect another. So this is A, B, C. Okay, then you can remove it. So get rid of B in this case. If that's not something that you care about. Right, but if you have something like this, then you can't get rid of it. Right? It can only affect another through your original variable.
You said these notes are going to be available, right?
Sorry?
These notes will be available on Canvas, you said?
The textbook will be available. I can post this handwritten stuff on Canvas, if you would like. In fact, I'll post these notes that's a little bit cleaner. But I'm not doing my regular LaTeX thing. But if you want more detail, you can get it from the textbook. She's probably a lot better at explaining than I am. Irrelevance. So if it's not part of the data generating process, or if it is part of the data generating process but not relevant to your research question, then you can remove it. Okay. So this kind of all has to do with the setup of the causal diagram. And what we want to talk about now are like paths. And the reason we talk about the paths that you go from one variable to another in a causal diagram is that is any path that you take from A to C, from D to C, B to C, whatever, that path represents like a plausible story for why your outcome variable changes or is affected. Okay, so let's take a look at an example of this. Right, I don't get an infinite whiteboard. Okay. So we're gonna look at something like this. So we have income, health, Okay. I want to understand how the consumption of wine may affect someone's lifespan. Okay, this is kind of like my research question. And my research question is really a causal one because I want to know, you know, if I increase my consumption of wine, how will that affect my lifespan, right? So that relationship is represented by this kind of line over here. Okay, I've written out a couple of other things. Health could also affect your lifespan directly, right? So if you are a person of poor health, that may cause you to have a lower lifespan and vice versa. Health could be in some ways related to the amount of wine that you drink. And so let me give an example here. So you have a data set and you observe that let's say a group of really healthy people, they have the same lifespan as a group of, let's say, unhealthy people. And so what might your conclusion be about health and its relationship to lifespan?
No correlation.
Right, and so you might say actually that there's no correlation, but what if it were the case that all of those healthy people in that data set drank an obscene amount of wine? Okay, so then would it be the wine that's leading to the no difference in lifespan compared to not healthy people? Or is there no actually effect, right? So we're not sure, but we can hypothesize that there might be something through here. And if there's something through here and you didn't control for wine, you might come to the wrong conclusion, okay? And I'm gonna just draw a couple more arrows here. Yeah, and so the U are unobserved variables. Maybe these are variables that we just don't have data on, but we know or we hypothesize that they could have some effects on income and health, and so the way that we would figure out any of the influence of these variables on each other, one of the things we'd have to make sure is to make sure to include that in the paths that we're trying to measure. So again, at the end of the day, we are concerned with these two as our treatments and outcome variable. So this treatments variable and our outcome variable. And what we actually want to do is we want to be able to find all of the paths in this diagram that we've set up, okay? So we set up this diagram by hypothesizing specific relationships, okay? And once you've done that, you want to find all of the paths. And there's like a specific procedure to do this. So finding all paths. So 1, start at treatment variable. 2, follow one of the arrows in/out of the treatment. To find another variable. Three, follow one of the arrows in/out of that variable. 4, repeat 3 until you find the outcome. Or a variable that you already visited, in which case that's a loop, not a path, and we want to avoid, right, this is acyclic, so we want to avoid that. So every time you find a path/loop, back up 1 and try a different arrow. Okay? All right, so let's find all the paths together. Who's gonna help me out here? Who can point out the first path? Maybe the most obvious path. Yes.
Income to lifespan.
We're starting, okay, step 1.
Excuse me.
What's step 1? Start at the treatment variable. So what's our treatment variable? Wine. So try again. We're starting at wine.
Wine to lifespan.
Wine to lifespan. There we go. Okay, so path 1. Wine to lifespan. Okay. We did it. We go all the way to step 5. We found a path. Back up. Try a different arrow. Okay, so instead of the arrow going to lifespan, we want to try a different arrow. Does anyone want to help me out here?
Wine, drugs, lifespan.
Yes, wine, drugs, lifespan. Wine to drugs. There's only one choice out of drugs. That's lifespan. I'm gonna go to step 5. I've finished the path. Back up 1. I'm gonna go to drugs. Are there any arrows that we haven't done? No. So then I'm gonna back up 1 more, and I'm gonna go back to wine. Okay. What else?
Income, lifespan.
Income lifespan. Great. So notice that it's an arrow going into wine, so it'll look something like this. Income going to lifespan. Great. What else? Who else can help me? Yes. Except we all start with wine, but yes. So that would be kind of the same thing. Wine, health, lifespan. Great. How else can we get from wine to lifespan? I see you doing a big motion, so help me out here.
But we can't counter the direction we are, right?
No, yeah, so, right, this is going this way. So you can go in or out of wine. So if I'm starting at wine, how do I get to lifespan a different way? You were showing me.
Yeah, but, so where's the line?
So, sorry?
Income, line, health, lifespan.
Okay, so income, and then
UI.
U1,
Mm-hmm.
yep, U1 goes to health, and this goes to lifespan. Do we have any more?
The opposite, going wine, health, UI, income, lifespan.
Yes. Wine, health, U1, income, lifespan. Okay. And, okay, again, right, each path here kind of represents a plausible story for how our outcome is affected by variables, right? So wine may have a direct effect on lifespan. Wine, let's say someone who drinks lots of wine also takes lots of drugs and affects their lifespan through that, right? And similarly, for any one of these paths, you should be able to generate like a plausible hypothesis, plausible story of how these things affect your outcome through a variety of these variables, right? So if I were to just control for wine and lifespan, and maybe even all of this stuff, but not for drugs, right? Any conclusion that you're making about the effect of wine on lifespan is getting muddled with a potential effect that's not being controlled, okay? So this is the equivalent of closing the door for the dog to get out, okay? So you want to control each of the doors or close the doors on all of any of your potential pathways, okay? Questions? So there's a bunch of different path types, and I will write these out. So path types. Okay, so you have a good path. So this is a path that relates to your research question. So this is a path that you are trying to identify. So in the previous example, the path that we are trying to identify is wine, is how you might get from wine to lifespan. Okay, and any of the paths that we're doing, because they all relate wine to lifespan, those are all good paths. A bad path is a path unrelated to your research question. Okay, and so that might be like a variable that goes into lifespan, but is not related in any way to any of those variables that we saw in our previous diagram. You have a front door path. So a path where all arrows point away from treatment. Okay, and if I were to look over here, which of these 6 paths are front door paths?
Two.
1 and 2, that's right. Front door, right? The arrow is pointing away from my treatment, that makes it a front door path. A backdoor path is a path where at least one arrow points towards the treatment. Okay, so that would be all of these guys. Backdoor, 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 backdoor. All of the arrows are pointing, or there is at least one arrow pointing into your treatment for each of these. An open path a path in which there is variation in all variables along a path. And a closed path is a path in which there is at least one variable with no variation. Okay, so let's think about what this means. So So let's forget about income, health, and U1 for a second. Let's imagine your diagram is wine, lifespan, and drugs. And that's like the whole world, right? Just wine, lifespan, and drugs. And I want to understand the effect of wine on lifespan. Okay. So if you have variation in wine and some variation in lifespan, and you have variation in drugs, then there's stuff happening here, there's stuff happening here, and there's stuff happening here. So whatever is happening with wine, these are all open paths for an effect to happen, right? For one of these paths to cause an outcome. And so if lifespan is varying up and down, I don't know if that's because of the variation in my drugs or if that's because of the variation in the wine that's being taken. Does that make sense to everyone? If I somehow close a path and eliminate the variation, that would be the equivalent of I have variation in my wine and I have variation in my lifespan, but there's no variation in drugs. Okay, so what does that mean about my ability to conclude something about the effect of wine on lifespan? Right, yeah, it means that we can be certain that the drugs aren't doing anything because the drugs actually aren't changing in any way. So that's kind of the fundamental thought process behind this idea of like open paths and closed paths. Once you close a path, that lets you make conclusions about what other open paths are doing in terms of changing the outcome. Okay? Is everyone following? Okay. The last kind of caveat thing to mention, this is kind of tricky to think about. There's something called a collider variable. So collider. So this is a variable along a path if both arrows on either side of it point at it. Oh, sorry, before I get to collider, so the way that we close a path is we like control for variable, right? So you like control for drugs and you prevent it from doing a variation. So the whole idea is to get to a causal effect, I want to control for certain variables in order to close the path and get an understanding of only leaving the path that I want to measure open. Okay, so controlling variables is the way that we close a path. That brings up this point, which is the collider. So the collider isn't actually an example that we had in the previous one, but it looks something like this. So treatment going A, B, C, outcome. Okay. So which variable is the collider variable?
B.
B, exactly. Both arrows are going into it. Okay, and that's not something that we actually saw in our example. So let me do this. So it turns out that if you have a collider in a path, that path is closed by default. If you control for the collider, you actually open the path up. Okay, so that's just like one nuance to remember here. Closed by default. If you wider. The path opens. Unless you control for another variable in the path. All right. So the stuff that we covered here is a lot more conceptual than most of the material in the rest of this course, but it's kind of purposefully done so, right? Because this causal stuff is not something that is like more of like a plug and chug equation, right? So this requires like careful thinking and hypothesis building in order to attempt to measure causality. And what I'm attempting to do here by giving you this causal diagram framework is to give you kind of a foundation for how to systematically think about approaching like causality. Because a lot of times, you know, people will have these data sets and they'll like, you know, throw variables into these equations and say, okay, we control for all these things, and you know, I'm gonna do some identification tests and tell you that like, okay, great, this is like a causal effect, right? But fundamentally, what you really want to do is systematically build up a hypothesis about relationships between variables that gives you, you know, this diagram that is a more kind of defensible option for showing like why certain things are related to each other, right? Because each of these has like some plausible explanation, and then you can systematically show how you've controlled for each of these things. Now it is difficult, right? Because we're talking about, you know, you want to control for lots of these things, like how are you going to deal with this problem about U1, which is like these unobserved variables. And so next time, we're going to look at a couple strategies that kind of build off of this foundation. And these strategies are meant to like really empower you to essentially control for lots of things in certain ways that better allow you to look at this direct path thing. Yeah, and so we'll get into some of those tools next time, and we'll see examples of how you implement them in R. Okay. Yeah, that's it for today, and I'll see you guys on Monday.